All right, guys, so this is the final video for chemistry, so congratulations for making it this far. So what I'm going to do for this final exam review, I know it's a long review, it's a lot of material because it's the whole semester. I'm going to split it up into two parts, so I'm going to kind of split it in half, and then I'm going to kind of shotgun through it. Okay, so if you want more detailed answers for like the definitions and stuff, you can refer to the key. So if you need that, I'm going to kind of go through just the gist of it and kind of what you need to know. And then I'm going to kind of go through it as quick as I can. So if you need to pause, rewind, fast forward at any time, you can do so. So we're just going to go ahead and get started. So if you're doing this, if you're working on this with me and you want to kind of stop, pause it, and then do it yourself, you will need a periodic table, calculator, polyatomic ion list. So all that stuff kind of handy. So we're going to go ahead and get started. So we're going to start with some definitions. So I'm going to keep these short and sweet. So you're not writing too much. You can get more from the key if you want it. So we're going to start with an anion. So this is going to be a negatively charged ion. Okay, and these are usually going to be your nonmetals. So nonmetals are on the right side of that staircase on your periodic table. Okay, so an example of that would be like Cl minus. Okay, a cation is going to be your positively charged ion. And these are usually going to be your metals. So those are on the left side of that staircase on the periodic table. So this would be like something like Na+. Okay, a chemical bond, that is just the attraction between two or more atoms. Okay, so there's multiple types of chemical bonds. So I don't really have examples for that. I just put out many types. So they all basically deal with sharing electrons or taking electrons, and we're going to get more into that as we get into this unit. A formula unit, so this is just a molecule formed from an ionic bond. Okay, so a molecule formed from an ionic bond. Okay, so something like this would be like NaCl. Okay, our ionic bond. So ionic bond is the attraction between ions of opposite charge. Okay, so the attraction of ions of opposite charge. Okay, so when you take like Na plus and Cl minus, they're going to have that attraction that come together to make NaCl. Okay, so a monatomic ion, this is an ion with one atom. Okay, so ion with one atom. Okay, so what we mean by that is like K plus, Br minus is just one element, one atom by itself. Oxidation number is just simply the charge of an ion. Okay, so like when you see the +1, -1, those are going to be your oxidation numbers. Okay, polyatomic ion, those are things like you see on your polyatomic list. They're just two covalently bonded atoms. Okay, you can kind of bear with my hand right now. I'm kind of sitting in a weird position right now. Okay, so something like this would be like chlorate, so ClO3 with a minus. Okay, or phosphate, PO4 with a -3, that would be a polyatomic ion. Okay, properties of ionic compounds, so this would be something, so this would be a high melting point and boiling point. Okay, so it takes a lot more energy to break up ionic bond. It has high IMFs. So remember, those are your intramolecular forces. Okay, so those are basically the things that are holding it together. And then they also make a crystal lattice structure. Okay, so lattice is like the kind of checkered thing you see at the top of fences that vines grow through. That's what a lattice structure looks like. Okay, moving on to number 1. Ionic bonds occur between what two types of elements? This is going to be metals and nonmetals. Okay, so left side and right side. So to give the correct formula, for the following ionic compounds. So this is where you kind of need your periodic table, because the way I do this is based by charge. So every time you want to know a formula, you have to balance based by charge every single time. So like this, calcium iodide. So calcium is Ca with a +2. Iodine is I with a -1. Okay, I can see that those are not balanced, so you can do your crisscross. So this would be CaI2. Okay, magnesium is going to be a +2. Nitrate is a -1. Okay, so they're not balanced. So I'm going to need 2 nitrates. So this is going to be Mg. And I'm going to put NO3 in parentheses with a 2. Copper 2 chloride. This 2 right here tells me the charge of copper. Okay, so that means it's a +2. Chlorine has a charge of -1. So I'm going to need 2 chlorine. So this would be CuCl2. Sodium phosphate. Sodium is a +1. Phosphate is PO4 with a -3. So I'm going to need 3 sodiums to balance out that 1 phosphate. Okay, zinc phosphide. So zinc is +2. Phosphorus is -3. Okay, so this comes out to, I'm going to do your crisscross. So this becomes Zn3P2. Aluminum carbonate. So aluminum is +3. Carbonate is Al2. Carbonate is CO3 with a -2. So you have a +3 and a -2. So I need 2 aluminums. And I'm going to need 3 carbonates. So I'm going to put CO3 in parentheses with a 3. Okay, manganese 4 oxide. Okay, so manganese 4, so that means it's a +4. Oxide is -2. Be careful with your crisscross here. You don't want to do Mn2O4, because if it can be reduced, it'll be reduced. So that means I need 2 oxygens to balance out that 1 manganese, so it should be MnO2. Okay, so just be, if it can be reduced, you would just reduce it. Potassium is a +1. Sulfate's a -2. So this would be K2SO4. Okay, 3, name each of the following ionic compounds. So here, we're not using prefixes. That's only for covalent, so that's something that's coming up. Okay, so this is just simply naming. So remember, we use things like "ide" on the end of it. Okay, so we're going to go through here. So the K2O, this would just be potassium oxide. FeCl2, so this is where you have to watch out, is iron is a transition metal, so it's kind of in that middle group. So you do not know what the charge is, so you have to look at who it's bonded with. So I have 2 chlorines that each have a charge of -1. So if I have 2 of them, that means that's a total charge of -2. That means if I have 1 iron to balance that out, it would have to be a charge of +2. So this would be iron 2, in parentheses with Roman numerals, chloride. Okay, next one, this would be just magnesium sulfide. Ca3P2. Okay, so this is going to be calcium phosphide. ALN, this is just going to be aluminum nitride. Na3PO4, this would be sodium phosphate. CrOH3, so chromium is a transition metal, so that means we do need a Roman numeral, so we need to find the charge. So hydroxide has a charge of -1. So if I have 3 of them, that gives me a total charge of -3. So that means chromium would have to be a +3 to be balanced out. So this would be chromium 3, so Roman numeral for 3, hydroxide. Last one is going to be barium nitride. Okay, moving on to covalent compounds. So a covalent bond, this is basically when we share electrons. Okay, and this is between, there should be an E with a minus charge. That's my abbreviation for electrons. Okay, this is between a non-metal and a non-metal. Okay, so an example of that would be, so you'd need 2 things from the right side of the staircase. Okay, so this would be something like CO3. Okay, diatomic molecules, these are atoms that are normally in pairs, so they cannot be alone. So atoms normally in pairs. Okay, so this is what I mean by, I'm just kind of giving you the gist of these definitions. If you want more definition or you want more detail, I usually have my students just paraphrase it. You don't have to write out the entire key. You can if you want. But I'm just kind of giving you the gist so you know what each kind of term is. Okay, so my diatomics, the way I'd remember this is Brinkelhoff. Okay, so Br, bromine, iodine, I, nitrogen is N, chlorine is Cl, H is hydrogen, O is oxygen, and F is fluorine. So Brinkelhoff. Okay, a Lewis structure. So then we might need to shake some rust off on some of this here in a bit. A Lewis structure is when we basically have a compound basically drawn out as what it would look like with bonded atoms and bonded electron pairs or free pairs like this. Okay, so that is what I'm basically going to write for my description. We'll do more practice on that here in a minute. Okay, valence electrons. These are going to be your outermost electrons. So basically the max number is 8. Okay, so if you look at the top of your periodic table, that's where you get that. You get the 1A, 2A, okay, and then you go all the way to 8A. Okay, so that helps you determine your charge is by looking at the valence electrons. Okay, octet rule. Okay, this basically means that atoms typically bond to achieve 8 valence electrons. So atoms will bond to have 8 electrons. Okay, so they all want 8 valence electrons. So this is why they make those shares, those bonds, is to achieve that. Whether they need to share electrons or take them, that's what they'll do. Okay, so for covalent bonds, whenever we do our naming, we use our prefixes now. So when we do covalent, so our prefixes are going to be mono, that's 1. 2 is di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. And 10 is deca. Okay, so we will use those here in a minute. Okay, lone pair of electrons, that is just electron pair that's unbonded on the Lewis structure. Okay, so what I mean by that is when the one I had up here, so I got oxygen bond with 2 H's and I had 2 lone pairs right here. These are lone pairs right here. They are just unbonded pairs of electrons. Okay, polar covalent versus non-polar. So remember, polar and non-polar. So polar means you have a positive side and a negative side. Okay, which makes this not symmetrical. Okay, so I'm going to draw one out. So if I had one like this, so N in the middle with 3 hydrogens bonded, and then I had a lone pair right here. Okay, this is not perfectly symmetrical, so that means you're going to have a slightly negative side compared to the other hydrogens. So this would be polar. Non-polar is basically when you have, it's just even all around. So this would just be symmetrical. Okay, so that would be symmetrical. So an example like that would be like this. So carbon in the middle with a chlorine over here, chlorine here, and chlorine here. Okay, so everything's nice and symmetrical. Okay, VS or Vesper model stands for valence shell electron pair repulsion. Okay, so basically what this means is that electrons will push each other away. Basically creating a shape. Okay, so these electron pairs do not want to be near each other, and so when they push each other away, it creates a geometrical shape. Electron domains, this is basically the number of things attached to the central atom. Okay, so this could be a shared pair. Okay, so shared pair of electrons, which would be like a line, or a not unshared pair. So this would be like your 2 dots. Okay, so those both count as a domain. Okay, so if I had an example, I'd do like this. So N with an H. So I'm going to do 3 H's. So this would be NH3. And I have a lone pair right here. So I have 1, 2, 3 hydrogens. And I have an unbonded pair. So this thing would have 4 electron domains. Okay, hydrogen bonding. This is when you have a hydrogen that is bonded to an N, O, or F. Okay, so if you have a Lewis structure where you see H bonded to an N or F, I just remember HNOF. Okay, that is a hydrogen bond. Properties of covalent compounds. Okay, so covalent compounds are not going to be as strong as ionic compounds. So they're going to have low melting point and boiling point. So it's not going to take as much energy to break them up, which means they have low IMFs. So the bonds there are just not as strong. Okay, so we're going to move down. We have a few more on this one. On my key, so you can kind of refer to the key on this one. I didn't bother kind of doing this one because you get the geometry structures. So this is just kind of, if you want to know, just kind of look at the chart. So as we get into this next one, you can have your geometry structures out to kind of see where I'm going with this. Okay, that would probably help you out. So we're going to go into Lewis structures now. So we're going to start off with the first one. So remember, we might have to shake some rust off on this. We have to find valence electrons for each one of these. Okay, so this is where you get to see the 1A, 2A, 3A. Just look at the top. So hydrogen is in the 1A group, but there's 2 of them. So that means there's 2 valence electrons for hydrogen. Oxygen is in that 6A group, so it has 6 valence electrons. There's only 1 of them, so it's 6. What you do now is you add those up, and that means you have 8 total valence electrons. What you do now is you're going to divide that by 2, which gives me 4 pairs. Okay, first thing I'm going to do is hydrogen can never be in the middle. Okay, it can only hold 1 pair. So that means oxygen has to be in the middle. Okay, and I'm going to bond 2 H's. That's my first step. Okay, so I just used up 2 pairs right there, so I have 2 left. So that means since hydrogen can't hold anything more than that 1 line, those 2 unbonded pairs are going to be my last 2 pairs. So if I want to look at the total number of electron domains, this would actually be 4. 2 hydrogens and 2 unbonded pairs. Your electron domain geometry is like your base shape. So then you're going to look at the electron domain geometry on your chart, and 4 would be tetrahedral. Okay, then you're going to look for the ones that has 2 unbonded pairs. Is basically the 2, it looks like basically the big balloons on your chart. Okay, so you've got looking for the one with 2 atoms and 2 big balloons. So this would be a shape that's called bent. Okay, and this is not symmetrical because these hydrogens actually bend. Okay, meaning you have a negative side here and a negative side here, and it makes these hydrogens more positive. So this is not a symmetrical charge. So this would actually be polar. Okay, CCl4. Okay, so carbon is in group 4A, so it has 4 valence electrons. Chlorine is in group 7A, but I have 4 of them. So 7 times 4 is 28. Add that up, and you get 32 electrons. Divide by 2, and you get 16 pairs. Okay, what I'm going to do is I'm going to put carbon in the middle, and I'm going to bond 4 chlorines. So I just used up 4, so I have 12 left. So I'm going to start on my outers. I'm going to put 3 on each. So 3 electron pairs on each one. So there's 3, 6, 9, and 12. So I just used up all 16 pairs. So this one has also 4 electron domains. So this would also be tetrahedral. Okay, and there are no unbonded pairs, so the name is just going to be the same for molecular geometry, so this would also be tetrahedral. Okay, and this is perfectly balanced out, so this would be nonpolar. Okay, BH3, so boron is going to have 3 electrons. Hydrogen is going to have 3. Add that up, you get 6. Divide by 2, and I have 3 pairs. So what I'm going to do is I'm going to take boron, okay, and then add an H. Add 3 H's. I just used up 3 pairs, and that is it. Okay, so remember, boron is one of those exceptions. Boron is fine with 3 pairs. Beryllium would be fine with 2 if you see that. So boron does not need to have 4 pairs. But if you were starting at carbon, so when you start at carbon, you have to have at least 4 pairs. So that's when double bonding kind of goes through, which we'll do here in just a second. So I'm going to look at how many things are attached. There would be 3 things attached. So the electron domain geometry would be called trigonal planar. Okay, and then since there's no unbonded pairs, it's just going to have the same name for your molecular geometry, so trigonal planar. Okay, and this is going to be balanced out, so this would be nonpolar. Okay, N2. So what we're going to do is we have nitrogen, okay, which is in the group 5A, and I have 2 of them, so there's 10 electrons. So 10 divided by 2 gives me 5 pairs. Okay, so the first thing I'm going to do is I'm going to bond 2 ends to each other. Okay, so you're going to have to choose one of these to kind of fill up first, and then the other one's going to get the leftovers. So I just used up 1, so I'm going to fill up this left one with 3. So I've used up 4 so far, and now I've got 1 left, so I'm going to have to put on this nitrogen. So if you look at this, one nitrogen's getting the good deal, and one's not. Okay, so what's going to happen is you're going to have to move 2 of these pairs over to share between the nitrogens. So these become a triple bond. So that way each nitrogen is going to have its 8 pairs. Okay, so let me erase this, kind of clean this up. I'm going to have to fix that. So your correct Lewis structure would look like this. Okay, so here, if I only have 2 atoms basically attached to each other, this can only be a domain of 2, or electron domains of 2, which makes it linear. Okay, and the shape for linear is always going to, the electron or molecular geometry is always going to be linear when the electron domain geometry is linear. Okay, this is balanced out, so this would be nonpolar. Okay, NH3, so N has 5, H has 3, add that up, you get 8. Divide by 2, you get 4 pairs. So I'm going to take N and bond it with 3 H's. Okay, I just used up 3. I have 1 left, so that only can go back on nitrogen. So if I look, I have 4 things attached. So this is going to be tetrahedral. Okay, I have 1 unbonded pair, so you're looking for that 1 balloon. So that's going to be trigonal pyramidal. Okay, and this is not perfectly balanced. You have this big negative electron pair right there, so this is going to be polar. Okay, number 3, ion dipole, hydrogen bonding, dipole, and London dispersion. Okay, so these were basically like our IMFs that we were going into whenever we did Lewis structures. Okay, so I'm going to start actually at the bottom. Okay, because London dispersion is going to be your weakest. And then as you go up, they get stronger. Okay, so basically all bonds are going to have some form of London dispersion. Okay, so all bonds have London dispersion forces. Okay, that is basically when you have an electron attracted to a proton of another atom. Okay, so they're all going to basically do this. Okay, so this would be for both nonpolar and polar Lewis structures. Okay, dipole, this is going to, when you have a positive end of one molecule is attracted to a negative end of another molecule. Okay, and this happens in polar molecules only. So you have to have you have to have those positive or negative poles in order to have a dipole bond. Hydrogen bond, this is simple. So remember, if you have hydrogen bonded to N, O, or F, that makes it a hydrogen bond as well. Ion dipole, this is also when you have a positive end, okay, attracted to a negative end. But ion dipole usually happens between ions in a solution. Okay, so basically you would see something like AQ. So a good example of an ion dipole would be something like salt water. You have a positive sodium molecule attracted to the negative ends of H2O molecules. Okay, so the big thing is looking for the aqueous sign. Okay, that would indicate an ion dipole. So that's kind of the big difference between ion dipole and dipole. Okay, number 4, covalent bonds occur between what two kinds of elements? This is going to be a non-metal and a non-metal, so both on the right side of that staircase. The way I remember that is covalent almost sounds like coexist, so they're both on the right side. Okay, so this is when we use our prefixes. Okay, so in F3, so we never use mono on the first one. You can use mono on the second one, but we do not use mono on the first one, so this would just be nitrogen. And 3 fluorine, so this would be trifluoride. Next one would be silicone tetrafluoride. Next one would be selenium dioxide. Okay, now we're actually getting into some numbers for the first one. So this would actually be penta-oxygen. So we do not change that first name. We just add penta. And then trifluoride. Okay, the next one would be sulfur hexafluoride. Then you have diphosphorus. And then heptaoxide. Then you have nitrogen monoxide. Okay, and then you have xenon tetrachloride. Okay, write the chemical formula for each of the following. So now we can actually look at this. So sulfur, if there's nothing there, that means it's just mono, so that would just be 1 sulfur. Difluoride, di is 2, so this would be SF2. Next one, carbon tetrafluoride, so this would be C, and then F4. Ammonia is just NH3 with a positive charge, so that's kind of just thrown in there. That's usually just take away one of the H's from ammonium, and that's how you get that. Trinitrogen heptaoxide, so 3 N's, and then hepta is 7, so this would be O7. Carbon dioxide, so CO2. Phosphorus trichloride, so PCl3. Okay, naming acids. So this is probably one of the biggest units where we saw a lot of struggling with. So kind of make sure you're paying attention to this if you struggled with acids. So binary acids, remember, bi needs 2. Okay, so this is basically just hydrogen. So all acids start with a hydrogen. Hydrogen and 1 other element. Okay, we use the term hydro in the beginning. So the way I remember this is hydro equals no O. That means there's no oxygen present. So that would be something like HCl. Oxyacids are exactly what they sound like. You basically have a hydrogen bonded with some type of polyatomic ion that has oxygen usually present. Okay, so we're going to write that out. So hydrogen, okay, with a polyatomic. And we do not use hydro, so no hydro in the name for oxyacids. So this would be something like HClO3. Okay, so name these acids. So H2SO3. So one thing you kind of need to remember is when you're dealing with polyatomics, if it ends in 8, your acid will end in ic. If it ends in ite, your acid will end in us. Okay, so H2SO3. So 1, I see oxygens, so I'm not going to use hydro. And that is actually sulfite, so this would be sulfurous acid. H2SO4, so now we're actually doing a sulfate. So now this would be sulfuric acid. HF, so this is binary, so there's no oxygen, so I'm going to use hydro. I'm going to go ahead and start with hydro. And this would just be hydrofluoric acid. Next one, NO3 is nitrate. So this would be just nitric acid. HC2H3O2. So that HC2H3O2 is just acetate. So I'm not going to use hydro because it's a polyatomic. So this would just be acetic acid. HCl. I don't see oxygen, so I'm going to use hydro. So this is going to be hydrochloric acid. 2, write the chemical formula for these acids. So now we're actually writing the chemical formula. So phosphoric acid, I don't see hydro there. So that means I'm dealing with H+, and phosphoric means phosphate. So PO4 with a -3. So you make sure you balance out based on charge. So the correct formula would be H3PO4. Okay, phosphorus acid. So big thing there is ends in us. So that means I'm doing a phosphite. So remember, hydrogen has a charge of +1. Okay, phosphite has a charge of -3. So this would be H3PO3. Hydrobromic acid. So there you go. So hydro right there. So that means I'm dealing with just hydrogen, which has a charge of +1. Bromine has a charge of -1. So this would just be HBr. Okay, carbonic acid. So I don't see hydro, so I know I'm dealing with a polyatomic. Carbonic means carbonate, so this would be H+, and CO3 with a -2. So your correct formula would be H2CO3. Hydrocyanic acid. So this is where you deal with H+, and there's no oxygen present, so this would just be cyanide, so Cn with a -1. So this would be just HCN. Nitrous acid. So that means I'm dealing with nitrite. Okay, so that would be H+, and NO2 with a -1. That would be nitrite. So this would be HNO2. Okay, number 3, identify each of the following as ionic, covalent, or an acid. Okay, so ionic, remember, is a metal and a nonmetal. Covalent is a nonmetal and a nonmetal. And acid is just anything that starts basically with an H. Okay, so A is going to be an acid. Okay, and this is just going to be hydrochloric acid. Okay, B, lead 2 sulfate. So that lead's a metal, so this is going to make this ionic. Okay, the lead has a charge of +2. Sulfate has a charge of -2. So this would be PbSO4. So already balanced. N2O4, so they're both on the right side of my staircase. So this is going to be covalent, so you're going to use your prefixes. So this would be dinitrogen tetraoxide. Okay, magnesium, so Mg is metal. Hydroxide is non-metal, so this makes this ionic. So this would be just magnesium hydroxide. Okay, sulfuric acid. So we know this is definitely an acid. So acids always start with an H. I don't see hydro, so that means we're doing the polyatomic. So sulfuric means sulfate. So SO4 with a -2. So correct formula would be H2SO4. Okay, HNO2, this is going to be an acid because it starts with an H. NO2 is nitrite, so this would be nitrous acid. Okay, G, PCl3, so both are all going to be on the right side of that periodic table, so this is covalent. Okay, so this would just be phosphorus trichloride. H, carbon tetrabromide, so I can see tetra, so there's a prefix, so I know this is going to be covalent. So this would just be C, and then I have 4 bromines, so this would be Br4. Aluminum phosphite, so this is going to be ionic. Aluminum has a charge of +3. Phosphite is PO3 with a -2. I'm sorry, -3, sorry, those are already balanced. So this would be just AlPO3. Okay, phosphorus acid, so we know this is an acid. Phosphorus, so this would be H+, and phosphite, so PO3 with a -3. So this would be H3PO3. Hydrofluoric acid, so we know this is an acid. Hydro means there's no oxygen present, so this would just be H plus, and fluorine with a -1. So this would be HF. Okay, ZnCl2. So remember, zinc is always at a charge of +2. Okay, so it does not need a Roman numeral because it is not a transition metal. So this would just be zinc chloride. Fe2O3. Okay, so iron is a metal and is a transition metal, so this makes this ionic. Oh, sorry, L was ionic as well. Okay, so we need to figure out what the charge of iron is. So on this one, you could pretty much do a reverse crisscross. So the 3 would go up here and the 2 would go up here. This works if that 2 matches the charge of oxygen, which it does. Oxygen has a charge of -2. So that means iron has a charge of 3. So this would be iron 3 oxide. Okay, HClO3. Okay, so this is an acid. Okay, ClO3 is chlorate. So this would be chloric acid. Acetic acid. So again, this can be acid. So it starts off with an H plus, and this would be acetate. So C2H3O2 with a -1. So already balanced. So this would just be HC2H3O2. Okay, moving on. So we do have quite a bit of definitions here, but I'm going to try to shotgun through these. An aqueous solution, this is a substance capable of being dissolved in water. So can be dissolved in water. Okay, the usual way we determine that is through Cashingia, which we'll use here in a bit. Okay, law of conservation of mass. This is basically why we balance. Okay, so mass before has to equal the mass after. Okay, so if I have 3 hydrogens before on the left side of the reaction, I better have 3 hydrogens on the right side. Okay, and my next is coefficient. This is just the numbers we put in front to balance. That's your coefficient. So the numbers we put in front of the compounds to balance them out, that's what a coefficient is. A precipitate basically means it is insoluble or it is a solid. So meaning it will not dissolve in water. Okay, a reactant is going to be something on the left side of the arrow. Okay, a product is going to be on the right side of the arrow. Okay, activity series. So this is that chart you get on the back of that periodic table that has the big arrow going up and down with a list of metals. Okay, basically what we use this for is this determines if single replacement will occur. So remember, when you have a single atom trying to make its way into a compound, okay, it is only going to make its way in if it's better than the one that's already there. Okay, so that's what we use to determine single replacement. Solubility rules. So this is when we actually use our Cashingia. So C stands for chlorate. Okay, most of these are going to be on that polyatomic list. A stands for acetate or ammonium, either one. S is going to be your sulfate. H is going to be your halides, because that's in that group 7A. So that the way I remember that is Brickle. So bromine, iodine, chlorine. So those are going to be halides. And then you have A, the other A, which is ammonium. Then you have N, which is your nitrate. And then you have Gia. Okay, so that is your group 1A. So the far left group on that periodic table, starting with kind of going down in hydrogen. Okay, so if you're on that list, that makes you soluble. Okay, the only thing you want to watch out for is the bad guys. So this is when you have silver, lead, and mercury. Okay, if these are attached, the bad guys need to So basically, if these 3 are attached to sulfates and halides, it makes them no longer soluble. So it's going to make them insoluble, making them a precipitate. Okay, combustion reaction. So this is basically when you have a hydrocarbon. So something like that would be like C3H6, C2H2. Okay, and it's going to react with oxygen gas, and you're going to get the same products every time. You're going to get CO2 and H2O. Okay, that is a combustion reaction. Synthesis reaction is when you have two reactants make one product. Okay, so this would be like A plus B gives me AB. Decomposition is just the opposite. So to decompose, this is when you have one reactant makes two products. So it breaks down into pieces. So this would be like AB breaking down into A plus B. Okay, single replacement. This is when you have one element trying to replace another in a pair. Okay, so it has to be better. So you'd look on the activity series, and if it is higher up than what it's already bonded with, okay, then it will take its place. So this would be something like A plus BC gives me AC plus B. So this reaction actually happened. So remember, if A is not better than B, okay, C is not going to dump B just for no reason. So this would be a no reaction. Okay, double replacement. This is basically just when you have two pairs swap partners. Okay, so this is like when you have AB plus CD. Now you get AD plus CB. Okay, number one. So moving on to this. So write skeletal equations, balance, then classify the following equations as synthesis, decomposition, combustion, single or double replacement. So I have hydrogen iodide. So hydrogen is H plus. Iodine is I with a -1. Hydrogen right here. Okay, so I put these together. So this is going to be HI. This breaks apart into hydrogen and iodine. So remember your diatomics though, Brinkelhoff. So H cannot be by itself, so this would be H2. And I cannot be by itself, so this would be I2. Okay, so I can look at this and I can tell this is decomposition. Okay, I broke down into pieces. I have to make sure I balance now. I have two H's on the right, two I's on the right, and only have one of each on the left side. So all I'm going to do is put a 2 in front of that HI, and that fixes that for me. Butane, C4H10, so C4H10 plus oxygen gas. Oxygen cannot be by itself, so this is O2. Gives me carbon dioxide, which is CO2, and then water is H2O. Okay, so if you want to start off with it, you can balance this way. I'm going to do CHO. You do not have to do this. Okay, sometimes this helps on combustion though. I have 4 carbons on the left, 10 hydrogens on the left, 2 oxygens on the left, 1 carbon, 2 hydrogens, 3 oxygens. So I'm going to fix carbons first. I usually like to save my oxygens for last. So I'm going to put a 4 in front of this CO2. So that fixes my carbons to 4. But if I look at my oxygens, 4 times 2 is 6, plus that 1 on H2O gives me 7. So now I'm going to move on to hydrogens. I have 10 hydrogens on the left, only 2 on the right. So I'm going to multiply this H2O by 5. Okay, that gives me 10 hydrogens. Now I have to check my oxygens again. I have 8 plus 5 gives me 13. Okay, so now I need to get O2 to 13. Only way I can do that is multiplying it by 6.5. Okay, so that's okay. Okay, what I'm going to do now is, since I can't have 6.5 oxygens, I'm going to double it, so that becomes 13. But once I do that, I have to do that to everything. So this little imaginary 1 in front of butane becomes a 2. This 4 becomes an 8. And this 5 becomes a 10. And now it's balanced. Silver nitrate. Okay, so silver is +1. Nitrate is -1. So this would just be AgNO3 plus sodium sulfide. So sodium is +1. Okay, sulfur is actually going to be a -2. Okay, so I'm going to need 2 sodium, so this would be Na2S. Then silver sulfide, so +1, -2. So a correct form of this would be Ag2S. Plus sodium nitrate, so sodium is +1, nitrate is -1. So this would just be NaNO3. Okay, so when you balance, if you have polyatomics, I would keep them as polyatomics. So if I have nitrate right here, if I have nitrate over here, I'm going to keep them as nitrates. So this one, I'm just going to look through. I'm not going to do the actual writing out. I'm just going to look. I have 1 Ag on the left, 2 on the right. So I'm going to put a 2 in front of this AgNO3. So that fixes my Ags, but now I have 2 NO3s on the left and only 1 on the right. So I'm going to put a 2 in front of this. Okay, so now that fixes my NO3s, and I have 2 NAs on the right, 2 NAs on the left, 1 sulfur on the right, 1 sulfur on the left, so this one's already done. Okay, aluminum, if aluminum's by itself. Okay, plus iodine. Iodine's by itself, so iodine's part of my Brinkel-Haff, so this would be I2. Gives me aluminum iodide. So aluminum has a charge of +3, iodine has a charge of -1. So this would be AlI3. Okay, so I'm going to take a look at my balancing. So I've got 2 iodines on the left, 3 on the right. So what I'm going to do is I'm going to multiply the iodine by 3 to get to 6, and I'm going to multiply the AlI3 by 2 to get the iodines to 6, because 3 can't go into 2 and 2 can't go into 3, so I had to get them both to 6. Okay, so that fixes my iodines, and now I have 2 aluminums on the right, only 1 on the left, so I'm going to put a 2 in front of this. Okay, so looks like I also forgot to label out what type of reaction this is. So we go back up here, the butane one, this is going to be your combustion. My next one, it looks like I have 2 pairs, and then they swap partners, so this is going to be a double replacement. On this one, aluminum and iodine, I have 2 reactants making 1 product, so this would be a synthesis. Okay, next one, I have sodium, so this is going to be Na with a +1, so I don't really need that. Not right now, at least. So sodium would be Na plus magnesium iodide, so magnesium is +2, iodine's -1, so this would be Mgi2. Gives me sodium iodide. Okay, +1, -1, so this just be NaI. Plus magnesium, and magnesium is not a part of my Brinkel-Haff, so it's fine being by itself. So this would actually be a single replacement. So I have 1 Na on the left, 1 Na on the right, 1 Mg, 1 Mg, 2 I's, 1 I. So I need to put a 2 in front of this NaI. So now I need to fix my sodiums though. I need to put a 2 in front of this Na to fix that. Okay, identify each reaction as synthesis, so basically the same thing, and then just balance. Okay, I have 2 reactants making 1 product, so this is going to be synthesis. All right, I'm just going to do the type of reactions first just by looking at them. Okay, I have 2 pairs, so this is going to be double replacement. I have 1 lone trying to make its way into a pair, so it looks like it did, so this is going to be a single replacement. Then I have C2H4 plus O2 gives me CO2 and H2O. This is always combustion. And then Ag2O breaks apart, so this is going to be decomposition. Okay, so we're going to make sure we balance this. So I'm just going to do these by looking at them. Okay, so I have 8 sulfurs on the left, only 1 on the right. So I'm going to put an 8 in front of this SO3. That fixes my sulfurs. And now I have 24 oxygens on the right and only 2 on the left. So I'm going to multiply this by 12. Okay, so this is going to be a 112,8. Okay, so again, if you have polyatomics, keep them as polyatomics. And also one little trick I like to do is if I have OH and H separated, I change this H2O to HOH. You don't have to do this trick, but this is just something I do. So I have 1 aluminum on the left, 2 aluminums on the right, so I'm going to put a 2 in front of this. So that changes my aluminums. So now I have 6 hydroxides on the left and only 1 on the right, so I'm going to put a 6 in front of this HOH. Okay, so I'm no longer looking at this H2O. And now I have 6 hydrogens on the left, only 2 on the, 6 hydrogens on the right, 2 on the left, so I'm going to put a 3 in front of this H2SO4. That fixes that. And now I have 3 sulfates on the left, 3 sulfates on the right, so this is actually done. So this would just be 2, 3, 1, 6. Okay, aluminums. I have 1 on the left, 2 on the right, so I'm going to put a 2 in front of this. Fe is good. Oxygens. I've got 1 on the left, 3 on the right, so I'm going to put a 3 in front of this. So that fixes my oxygens. But now I've got to fix my iron, so I'm going to put a 3 in front of this. So this would be 2, 3, 1, 3. Okay, next one, I'm just going to take a look at this. I have 2 carbons on the left and 1 on the right, so I'm going to put a 2 in front of CO2. Fixes that. I'm going to look at oxygens last, so we'll get to that in a second. Hydrogens got 4 on the left, 2 on the right, so I'm going to put a 2 in front of H2O. Okay, so now I'm going to look at my oxygens. I have 2 times 2 is 4, plus 2 times 1, so 4 plus 2 gives me 6 on the right. And I only have 2 on the left, so I'm going to put a 3 in front of this O2. So this is going to be a 1, 3, 2, 2. Next one, I have 2 AGs on the left, 1 on the right, so I'm going to put a 2 in front of this. Okay, oxygens, I have 1 on the left, 2 on the right, so I'm going to put a 2 in front of this Ag2O. That fixes my oxygens, but now it also changes my AGs, so I'm going to have to fix that. So I have 4 on the left, so I need 4 on the right, so I'm going to put a 4 in front of the AG. So this would just be a 2, 4, 1. Okay, next one, identify each of the following as soluble or insoluble using solubility rules. So remember, this is where you're using your Cash and Gia. As long as you have 1 on the list and it doesn't deal with those bad guys, that makes you aqueous. If neither on the list, that is going to be solid or insoluble. I'm going to write soluble as AQ and insoluble as S for solid. Okay, NaCl. Okay, Na is in group 1. Chlorine is a halide, so both on the list, so this would be AQ. Calcium's not on the list, but sulfate is, so this would be AQ. Zinc is not on the list, and chlorine is on the list, and zinc's not a bad guy, so this is AQ. Chromium's not on the list, but nitrate is, so this is AQ. H2SO4, both on the list, so this is going to be AQ. AgCl, so remember you're looking out for these bad guys, so Ag, Pb, and Hg. So silver, lead, and mercury, if they're attached to sulfates or halides. So now AgCl, this is a solid because of that silver. Mg is not on my list, that's in group 2, and carbonate is not on my list either, so this is going to be solid. Okay, potassium is in group 1. Okay, so this is going to be aqueous. Iron's not on my list, sulfur's not on my list, so this is solid. Lithium is on my list, phosphate is not, but lithium is, so this is going to be AQ. Okay, both are on the list, HNO3, so this will be AQ. Hg is a bad guy, and it's bonded to a halide, so this is now a solid. Strontium is not on my list, and hydroxide is not either, so this is going to be solid. NH4, 2S, so ammonium is on my list, and sulfur is not, but as long as you have 1, that's aqueous. Copper is not on my list, phosphate's not on my list, so this is solid. Aluminum's not on my list, but chlorine is, so this is aqueous. Sodium's on my list, so this is aqueous. And cobalt's not on my list, and carbonate's not on my list, so this would be solid. Okay, moving on to the mole. Okay, so I am just going to go a little bit further on this. Yep, so just 2 more pages, and then I'm going to break this video, and I'm going to do the second part on its own, so we only have a couple more pages on the rest of this video. Okay, Avogadro's number, so remember this is when you have 1 mole equals 6.02 times 10 to the 23rd molecules, particles, atoms, formula units. Okay, so basically there's multiple kind of definitions for descriptions for that. The big thing is just having this number, 6.02 times 10 to the 23rd. Okay, molar mass, this is the mass of an element, okay, or compound, using your periodic table. Okay, that's all you're doing is find the mass of it using your periodic table. Mole is basically just an SI unit for the amount of substance. So instead of me using this giant number up here all the time, I can just say 1 mole. Okay, so it's just basically an easier way for us to simplify things. Okay, empirical formula. This is the formula in lowest possible ratio. Or basically it's just a simplified formula. So something like that would be like CH. Molecular formula is the true chemical formula. Okay, so that would be like maybe like C6H6. Okay, and then percent composition, this is basically just the percent of an element in a compound. Okay, the way we do that is we find basically the part or the element divided by the whole times 100. Okay, what are 3 types of particles that are represented by the mole? So remember we kind of talked about it there in Avogadro's number. It can be things like atoms, molecules, formula units, and I think I repeated myself, so that was it. Okay. 2, how many grams are in 1.58 moles of copper 2 nitrate, CuNO3 2? So this is where we get in, we start breaking into our dimensional analysis. So we always start with what we're given. Okay, so 1.58 moles of CuNO3 2. I'm going to draw my line. Okay, so remember this is where you carry everything but the number down to the bottom next. So that means I'm going to bring down moles of CuNO3 2. And now I'm trying to go from moles to grams, so I'm going to put grams of CuNO3 2 on top. I know that 1 mole equals the mass of CuNO3 2. So this is when you look at your periodic table and find the mass. Just be careful. These 2's on the parentheses, this actually cross multiplies over. So you have 2 nitrogens and you have 6 oxygens. Okay, so just add up your whole mass. So that should come out to 187.55 grams. Okay, anything on top you multiply, anything on bottom you divide. So just multiply those out. And if I start with 3 sig figs, just end with 3 to keep it simple. So this will be 296 grams. 3, determine the molar mass of iron 3 carbonate. So basically we're just finding out what is the mass of this. You have 2 irons. Be careful with this 3. You actually have 3 carbons and you have 9 oxygens. So add up 2 irons, 3 carbons, and 9 oxygens, and you should get 291.7 grams per 1 mole. 4, how many moles are in 55.8 grams of iron? So start off with what you're given. So 55.8 grams of Fe. Okay, that means grams of Fe is going to go on bottom. And this is how I can go to moles on top. So moles of Fe on top. 1 mole of Fe equals the mass of Fe. So that's going to be 55.8 using my periodic table. So divide 55.8 divided by 55.8, and that gives me 1 mole of Fe. Okay, so last page before I break this up into the next video. 5, how many atoms are in 3.50 moles of gold? So you're going to start with 3.50 moles of gold, so which is Au. And I want to know atoms. Okay, so I'm going to bring moles of Au on bottom next. I know 1 mole equals 6.02 times 10 to the 23rd atoms of Au. Okay, I'm going to kind of fix that 3 real quick. Oops. Okay, so what I'm going to do is I'm going to multiply the top. So just be careful with this when you put this in the periodic table. I like to keep these in parentheses, okay, just to kind of keep things tidy. Okay, and that way you don't mess up your calculator. So your number should be 2.11 times 10 to the 24th atoms. Okay, 6, how many moles are in 1.88 times 10 to the 23rd formula units of calcium hydroxide? So I'm going to start with 1.88. Sorry, I cannot write right now. Times 10 to the 23rd. Oh my gosh. Okay, 1.88 times 10 to the 23rd formula units, okay, of calcium hydroxide, so CaOH2. Okay, that means formula units has to go on bottom next. And I'm trying to get to moles, so I know that 1 mole equals 6.02 times 10 to the 23rd formula units. So this is what I mean by keeping things in parentheses. It kind of helps tidy things up. Because if you were to take this 1.88 times 10 to the 23rd and divide it by 6.02 times 10 to the 23rd, sometimes your calculator can get confused on order of operations and give you the wrong number. Okay, so your number should come out to be 0.312 moles. Okay, 7, how many grams of helium are in a balloon containing 5.50 times 10 to the 22 atoms? So start off what you're given, so 5.50 times 10 to the 22 atoms. Okay, so atoms is going to go on bottom next. Okay, so, and we're dealing with helium. I know there are 6.02 times 10 to the 23rd atoms in 1 mole. Okay, but it wanted grams of helium, and I'm only in moles right now, so I'm not done yet. So that means moles of helium has to go on bottom next. And I know that 1 mole of helium equals the mass of helium, so that would be 4.003 grams of helium on top. So multiply everything on top, get a number, divide by whatever's on bottom, and you should get 0.365 grams of helium. Number 8, how many molecules of nitrogen gas are present in 5.75 liters of STP? STP is going to be bigger here in a second when we do gas laws. But right now it just means standard temperature and pressure. So the point is we also need to know that 1 mole equals 22.4 liters. Okay, so I'm going to start with 5.75 liters of nitrogen gas, so N2. And I want to get 2 molecules, so first thing I can do is I'm going to bring liters of N2 on bottom. I know that 22.4 liters equals 1 mole, so I've got to get out of liters and into moles first. Now I can get to molecules. I know that 1 mole of N2 equals 6.02 times 10 to the 23rd molecules. Okay, multiply everything on top, divide by the bottom, and you should get 1.55 times 10 to the 23rd molecules. 9, so last two. The composition of acetic acid is 40% carbon, 6.71% hydrogen, and 53.29% oxygen. Calculate the empirical formula for acetic acid. So when we do empirical formula, you are going to treat these percentages like grams, and we're going to convert each one to moles. So for carbon, we're going to do 40.00 grams. Okay, and you're going to do the mass of carbon on bottom, so 12.011 grams equals 1 mole. Divide that out and you get 3.33. Hydrogen, we're going to do 6.71 grams. Okay, you're going to do the mass of hydrogen on bottom, so 1.008 grams equals 1 mole. Okay, that comes out to 6.64. And then lastly, oxygen, you're going to do 53.29 grams. Okay, there are 15.999 grams of oxygen in 1 mole. I'm just getting these numbers from the periodic table. That comes out to 3.33. Okay, next step is when you see a lot of decimals, this should be a hint that, one, you shouldn't have to round that far. And you're getting a lot of decimals, so You're not done yet. You're going to find the smallest number. So in this case, I've got the two are the same. So if there wasn't, you just pick the smallest one. So I'm just going to pick whichever one. And I'm going to divide everything by the smallest number. So divide by 3.33. This comes out to 1. Divide this one by 3.33. This comes out to 2. Divide this one by 3.33. And this comes out to 1. So these are nice even numbers. If I landed on something like a decimal, so like 2 was now 2.5, I could not have 2.5. So what I would do is I would multiply everything by 2 just to fix that 2.5. But in this case, I do have all whole numbers. So that means I have 1 carbon, 2 hydrogens, and 1 oxygen. So that is your empirical formula right there. Okay, 10, calculate the percent composition of aluminum sulfate, Al2SO43. So basically it wants to know what percent is aluminum, what percent is sulfur, and what percent is oxygen. Okay, so if I were to add up 2 aluminums, I would get 53.96 grams. If I were to add up, so this is where you got to be careful, you have 3 sulfurs and you have 12 oxygens. If I were to add up 3 sulfurs, you would get about 96 grams. I'm just kind of rounding on this one just to kind of be quicker. Oxygen, I have 12 oxygens, so 15.999 times 12 gives me roughly 192. If I add all these up, I get a total mass of 342.17. So I have my individuals now, and I have my totals. So what I'm going to do is I'm going to divide everything by my total. So divide by 342.17. I'm going to do that to all of them. And I'm going to multiply by 100 to make sure that it's in percent mode. Okay, just divide 53.96 by 342.17 and multiply by 100, and you get 15.8%. I'm going to do the same for sulfur. You get 28.1%. And then oxygen, you get 56.1%. Okay, so that is how you do percent composition. So this is where I'm going to break the video, and then I'll do part 2, and so that way it just kind of breaks this up.